Okay, so this video is going to go over linearization. So, nonlinear systems are much harder to solve than linear systems. So, we can linearize a nonlinear system to approximate its behavior. So, the concept behind linearization, well, if we have a nonlinear function f, which is dependent on x and u, I'm going to say they're scalars in this case, then that f can be approximately equal to f evaluated at our equilibrium points, xe and ue, plus the derivative of f with respect to x. You find that, and then you take its values and you plug in xe and ue, evaluated at equilibrium again, and then you multiply that by x minus xe, or delta x. That is our perturbation from equilibrium. And then you do the same thing for your derivative with respect to u, evaluated at equilibrium, and then multiply it by delta u, that u minus ue. Now, we can get the derivative and evaluate it at its reference point. Like I said, that's going to be our equilibrium. And then I'm going to use a lot of times for shorthand, this evaluation at its reference point, I'm just going to say a line E to represent that for short. So if we write this out for a multi-state system where f is dependent on x1 to xn, a bunch of different states and a bunch of different inputs, u1 to um, well, we can just approximate that as f is approximately equal to all those states evaluated at equilibrium, all those inputs evaluated at equilibrium, plus the derivative of f with respect to each input evaluated at equilibrium, or each state evaluated at equilibrium, multiplied by that perturbation of the state, x1 minus x1e, xn minus xne, and do the same thing for all your inputs here as well. So states are inputs, you're doing the same exact thing. And then you can choose something other than equilibrium to linearize about. However, in this class, almost always we're going to linearize about equilibrium because it has special properties for analysis. So what are the steps for linearization? And this ties into equilibrium as well. So the first thing that we're going to do is get our equations in state space form. X vector dot is equal to f vector, which is dependent on x and u. Y vector is equal to g vector, which is dependent on x and u as well. That's our outputs. And then we're going to solve for our equilibrium conditions. So we're going to set x vector dot is equal to 0, figure out what that function should be and what all our values xe, ue, and ye should be in this case. And then we're going to define our perturbations. So all our perturbations, we can represent that as a vector. It's just our current states minus, or our actual states minus our equilibrium values for those states. Same thing with inputs, same thing with our outputs. Now, the last step is to determine the linearized state space model. So in this case, x vector dot, which is equal to that function f of x and u, we can approximate that as our the same equation as using the same equation that we had before. So we evaluate f of x at equilibrium, but we know since we're evaluating at equilibrium, it's going to be equal to 0. But we're going to move over to the other side just in case. That is going to be added to the derivative of all those states, the derivative of the function with respect to all those states evaluated at equilibrium, very important that you evaluate at equilibrium or your reference point, and that's going to be lumped together into a matrix A. Multiplied by our perturbation vector for our states, we do the same thing with our inputs to get B here, another matrix that's going to be multiplied by delta U. And now, very much once we move this guy over here, we'll get that delta x dot is equal to A times delta x plus B times delta U. That looks like a linear system right there. We're going to do the same thing for our output equation. So again, we evaluate at equilibrium. We're going to move it to the other side. So we're going to get delta y vector. Notice there's no dot because there's no derivative for an output. It's just a static equation. And then we're going to get our C matrix, which is the derivative of our output functions with respect to our states, and our D matrix, which is the derivative of our output function with respect to our inputs, and then just plug them in here, and we end up with this equation. So this is what our linearized state space model looks like. Delta x vector dot is equal to A times delta x vector plus B times delta U vector, where and y delta y is going to be equal to c times delta x plus d times delta u. Now we're going to define four matrices here, where n is going to be the number of our states, m is the number of our inputs, and p is the number of our outputs. These are what these matrices from the last page are. It's going to be the derivative of the first function with respect to our first state evaluated at equilibrium. And then we pretty much keep going down the line until we get to our first function derivative with respect to our last state evaluated at equilibrium. And then we just keep going down the rows and keep evaluating this to get all of these matrices here. So all these are matrices are just a bunch of derivatives from our nonlinear functions that we had before. And that's all it takes to linearize your system.